Hello and welcome to our presentation on the Recipe Maker. So there are a few things that we're going to talk about today. We'll start by talking a little bit about the opportunity that we saw for an interesting data science solution for the Recipe Maker itself. From there, we'll talk a little bit about the system architecture. We'll talk about identification and scraping of recipes, the indexing and storage of recipes, then the user query and ranking process where we generate ranked results and present them to the user, finally through a web interface that the user can use to interact with the rest of the system. And lastly, we'll leave you with a slide where you can go and play with our demo itself. So our project started with a rather simple idea. Has to do with something we all do almost every day, and that is eating. So we asked ourselves, why is it such a hard process to find a new interesting recipe that I can make now? And that is, with all the data we have around us, why can't my kitchen help me find a recipe that I can make now with the things that I have, in the time that I have, and with the appliances that I have? So we built Recipe Maker as a data storage and retrieval prototype to start gathering some of the underlying recipe data that would be needed for such a system. And we'll talk a little bit about the scope of this project on the next page. So, because we started with an ambitious premise and goal, it was important for us to really define what we wanted to accomplish in the scope of this specific final project, which we view as just one building block towards solving this problem. So, our goal was to really take a first few steps forward and to generate a corpus of recipes that could be queried by a user based on some ingredients they have and using some relevant ranking criteria. So we set out to scrape a large number of recipe sites, including data both from structured and unstructured sources, where we view unstructured as something like a Twitter stream. We wanted to leverage parallel computing, some of the MapReduce framework, to process and index what we find. And then we wanted to build a quick query and ranking system that would provide a result in a reasonable time frame to the user. And we used a number of key tools in doing this, which we'll discuss throughout the rest of the presentation.
This diagram shows our system architecture. In the top left-hand corner, we start with Scrapy, which went to a list of known good web pages and scraped the recipes there. To do that, we used a bunch of homebrew scrapers that Rich wrote. And these scrapers went to the page and got a list of raw ingredients, which we stored in the Mongo database. The indexer, written by Joan, went to the raw ingredients and indexed that list. And then finally, a Python program put those items in a easy to query format and stored it back again into a Mongo database. From there, the Recipe Maker site was able to query the ranked recipe list. The second path that we took was starting at the bottom left-hand corner. The Tweepy was used to look for the hashtag recipe on Twitter. This led to a list of recipe URLs, which we found the recipe using Beautiful Soup and NLTK. We used a good list of ingredients to identify just the words that were known as ingredients. And we also made a list of URLs that didn't have recipes so that we could look at them and make sure that our algorithm was working correctly. Once we had those ingredients, we stored it again to the Mongo raw ingredients table. We used a second indexer, again, just to look at rejected ingredients. But then from there on, it's the same path into the index ingredients collection, into the Python rank recipe, into the ranked recipe collection, and then again to the Recipe Maker site. We actually made two different lists of known ingredients. This describes what we did with our second one. We went to the food.com about page and got a list of 900 known ingredients from them. We stemmed these words so that things like red pepper would become two words, red and pepper, and words like green pepper, red onion would end up being single words that were stemmed. Then we removed this list and made sure we removed low value words like of and that didn't make sense. And then we used this list to identify the ingredients on pages found throughout Twitter. This This list wasn't comprehensive as our original list, so there are definitely some gaps in there that we want to fix in the future.
In order to obtain our recipes, we primarily used Scrapy, a Python library used for web scraping, in order to obtain them. We used Scrapy to develop a wide range of scrapers that we tried to implement over larger websites, that is, websites that contained larger quantities of recipes. For each of these websites, we built a single scraper that would stay inside that domain and that would crawl through and seek out recipes that we would like to extract and use. So once it found a recipe, it would extract the ingredients from it, and then it would load that into a Mongo database that we stored, or that we used MongoLab to host. So these documents that it would store in Mongo would contain an ingredients list, a link to the recipe, the title of the recipe, and also a feature for determining whether or not we had included that recipe in the index already. So what you see here is our settings.py file for our Scrapy scrapers. The thing that I'd like you to focus on is the item pipelines key. And in that, you can see that we had a pretty simple pipeline using Scrapy. All we would do is our scraper would initially follow links to more pages or areas of the website where it thought it could find more recipes. And when it found recipe links, it would push those links down the Scrapy pipeline to the next part. So after it found a recipe, it would go to the extract ingredients pipeline, which would just go in and search for ingredients based on our good ingredients whitelist, and it would, if it found them, it would extract them all and return that object and push it again down the pipeline to the Mongo writer pipeline, where all the data would be sort of cleaned and then input into our Mongo database. Here you can see an example of one of the ways that we use to extract ingredients. What we did to extract ingredients from all websites was essentially develop sets of heuristics that we could use to try to find ingredients in a recipe. These were generally sets of regular expressions that would just be compiled and sent through a loop to try to get a match. And if a regular expression started to match, then we would use that regular expression to extract all the ingredients, and in that manner we were able to extract good ingredient lists from our corpus of recipes. Here you can see some of the results of our Scrapy scrapers. We were able to extract approximately 230,000 recipes in the time that we had for this project, and this is only a partial sample of the sites that we scraped. As you can see, some of the red ones, those are websites that we had some issues with. As I said in the previous slide, we develop heuristics to find our recipes, but unfortunately they aren't perfect, and sometimes they led us in directions that weren't able to fully extract the recipes. Going forward, as we continue to work on this project in our own time, we think that we'd be able to extend it with some machine learning algorithms that would be able to be more successful at extracting extracting ingredients from some of these harder to scrape recipes. We also see, as in the myrecipes.com example, we went down a spiral or an infinite hole of links, and that's something that we could clean up by stopping at, say, a certain depth. And additionally, if you look at food.com, that's a very large website of recipes, and we'd really like to be able to scrape it. However, due to its size and some of the collection techniques, we aren't able to do so. We want to make sure that we're good stewards in our searching and make sure that we obey robots.txt. So we have to come up with methods that can ingest all those recipes, but while still being polite to the servers that are allowing us to do so.
This slide shows us the architecture for the real-time recipes that we got from Twitter. We started with a tweet which led to a particular site. In this example, it's food.com. From that site, we got a list of all the links on the page, made sure that the links stayed on the page and they didn't link to another site, compared it to the list of links that we already had, so that we were looking at only new links, and then we put it back at the start and continued crawling through the page until we had all the links on the site. Once we did that, we went to each page, we tokenized the words on that page using Beautiful Soup, and looked for the keyword ingredients. Then we added every word that we found after ingredients until we found a word like directions or preparations or instructions. And then we took the set of those words, compared it against our good list, and kept only the good ingredients, which we then stored into Mongo.
Now we will talk about indexing the ingredients. The goal for indexing is that for each ingredient, we want to create a list of recipe links that contain the ingredient. We use the MapReduce framework for indexing, and there are two main reasons for that. First, it allows parallel processing, which reduces the amount of time needed to index hundreds of thousands of recipes. Second, the shuffling phase of MapReduce framework would create a list of values for each key, which corresponds exactly to what we want for each ingredient. Now let's briefly go over the mapper and the reducer. The mapper extracts key ingredients from the list of ingredients we created early on, and emit the ingredient and document ID pair. The reducer returns each ingredient with the corresponding postings list of document IDs. We leverage some natural language processing techniques to clean up the recipes before indexing, such as removing stop words and applying Porter stemming algorithm to the ingredients to remove common endings of words. We also experimented other methods for indexing, such as noun phrase detection and including word position in the output. Both methods allow certain level of simplification in the querying side, but it was too memory intensive, so we decided to be lean and go with the simpler solution of indexing individual words instead.
So it was important for us to be able to rank the results of a user query before we presented the results back to them, to have some sort of order. And we came up with 4 different ranking metrics that we thought would be interesting and relevant to our project goals. The first was the idea of completeness, or with the ingredients that a user searched for, can an entire recipe be made? This would be valuable if a user wanted to specify a large number of ingredients and find things they could make now. The second idea was that of coverage, or how many of the user's terms are in the individual recipe result. For example, if a user has only a few terms, they might want to have all of those terms be inside the recipes that we give back to them. However, if they're searching with many terms, they might not necessarily want all of those terms to be used. The third ranking metric was uniqueness, which we modeled based on the idea of a TF-IDF ranking. This particular measure would give extra weight to more rare ingredients in the query, which would in theory hopefully better hone in on recipes that are a little bit more specific and nuanced. Finally, we used an absolute metric of rarity. This was defined at the document level and was designed in a way that would give preference to unusual recipes based on the individual ingredients that were used in making that recipe. So, with these 4 different metrics, we allowed the user to specify to us how they wanted us to weight these together, and we could use this feedback loop as a way to try and hone in on what different users find to be optimal. Here we see an example of the user interface. We have a prompt, a box where the user can type in ingredients, and 4 different sliders, one for each of the ranking criteria that we mentioned in the previous slide. The user enters their query, can set the sliders if they don't like the default, and they push the Eat button to generate recipes. The user interface was built using a Python package called Flask, which actually provides the full ability to build web forms and web interfaces. Flask works with several other packages that lets you create different views and templates and forms. to be able to operate with the user. Here on this slide on the right, you can see part of our environment. You can see a number of templates are currently shown, as well as forms and views. Down at the bottom, we have an example of routing, which tells the web server what page to display when a user goes to a particular web address. So here you see the index can be accessed in 3 different ways, either specifying index, or as a default with nothing, or with a current page, which is used in pagination of results. Now, it isn't enough to just build a web app. We also have to host it somewhere online where individuals can find it and then interact with it. For this purpose, we use a service called Heroku, which is fantastic. It's extremely easy to deploy to Heroku. You literally just push from your master branch to Heroku, and Heroku can handle the rest. You just need a few configuration options. Heroku has some great benefits. It'll store your code in what's called a slug locally, and when someone goes to the page, they spool up a dyno with your slug and very quickly have availability for that user, which is just a great process. We find a user goes to our site and they pretty quickly can start interacting with it. Heroku also interacts very well with Mongo Labs, which was where our data was stored, and that was another benefit to us that made us want to use this technology. Last but not least, we have the query process itself. Now, the key consideration in the query process was to try and reduce the amount of time spent searching for results. So we think we were very successful in doing that. The user typically gets a result back almost, what seems like instantaneously. So our process has 7 different steps, which are outlined here. First, the user has to select an input and slider values and send it to the query code. The query code will very quickly use the MongoDB to pull all of the postings that are relevant to that particular query. And in that posting list, we've already preceded a few elements of the ranking process just to save time calculating where possible. Once we have those posting lists, we really leverage dictionaries, this key value lookup, to really quickly do some post-processing of the partial ranks that were saved in the inverted index. So we do that, and we balance based on the slider inputs that the user specified, and we return a ranked list to the user. And this is just a list of document IDs at this point. The user's display will then store that locally as a cookie and look to see how many results and which results need to be displayed to the screen. The default is just to display 5 recipes at a time and to let a user scroll from page to page. So our system only really needs to get full document information for those 5 recipes. So once again, it will query the MongoDB, it'll pull the title and the web address of those 5 document IDs, and it will display them to the screen. And then as a user pages from page to page, the cookie information we've stored, when it's present, will allow the system to very quickly just get the next URLs and titles as opposed to rerunning the full query. Now, using a cookie in this matter definitely has downsides, and that's something to be discussed and addressed as and if this project continues forward. One of the great things about Heroku is it also provides you with a web address, so if you go to the link on this page, you can play around with our demo yourself.
Well, we're very pleased at the things we were able to do in such a short time on this project. We found that there are still lots of features that we'd like to add and lots of extending we'd like to do to this project. One of the big things we think we can do to improve it is to leverage machine learning techniques as we start to learn those. We can use that, as I said before, to aid in ingredient extraction, as right now we just have the regular expression-based heuristics, which do leave something to be desired. We can also extend it to start understanding the recipes we have by clustering ingredients, and using this we can form data structures that could give us some good insight into what kinds of things people eat. And finally, and obviously, a recommendation system is something that we'd like to add. As people go through and use the site, we'd like to be able to give them more ideas of things that we'd think that they would like and learn from them about what they'd like to provide a truly quality service to them. Our current implementation also could use a lot of search engine optimization techniques. The current technique of crawling through everything is somewhat inefficient in some regards, and we could use things like looking at the sitemap.xml to aid in our searching as well, or our indexing as well. We'd also like to be able to update the index rather than recreate it every time we add more recipes. Currently, we have to rebuild it every time. But as I stated in one of the earlier slides, we do have an isIndexed feature in our Mongo database to determine if something has been indexed already. We're not currently using that, but it's something that we think would be very important to incorporate in the future. We'd also like to come up with more advanced ranking systems for our recipes. We've started implementing some based on unique ingredients or complete ingredients, things like that, but we'd really like to take a deep dive and see what kind of neat features we can make for users.